This video is on trigonometric integrals that involve powers of sine and cosine. Integrals like these, the one you see on the screen, there's a definite strategy to apply to these, and we're going to try to develop that now. This isn't really a new calculus technique. These integrals just involve trig identities and u substitution, but we're going to develop a definite way to do them. And so let's start by looking at this problem. So if you look closely, the problem that I've got written on the screen is actually the same problem twice. And so we're going to look at two different approaches and see which one works better in this case. So most of the time when you have integrals involving powers of sine and cosine, what we would prefer is to do a u substitution where either u is sine x, in which case du would be cosine x dx, or we could try u equals cosine x, and then du would be negative sine x dx. And so we're going to proceed with both solutions. Only one of these works well on this problem, but we want to see what happens. So if you look at the first problem, or the first version, if you let u equal sine x, then we're going to try to get du at the end of the problem by doing this. We're going to leave sine to the fifth alone, but then cosine to the fourth x means that we have four factors of cosine, and we want one of them for the du. So we're going to take one of the four, and that leaves three factors of cosine. And then the fourth one is over here for the du. So we've got cosine to the third times cosine split up so that the extra cosine, the one on the end, is used for du. Now we need to rewrite everything in terms of sine because u was equal to sine over on the left. We can use the identity from trig that sine squared plus cosine squared is 1 to rewrite any power of sine in terms of cosine, and it will let you rewrite any power of cosine in terms of sine. So if we have cosine to the third, which is what we want to rewrite, we can think of cosine to the third as being cosine squared to the 3/2 power. Because when we raise a power to a power, we multiply. So cosine squared of x to the 3/2 would be cosine cubed of x. Based on the identity at the top, we can rewrite cosine squared as 1 minus sine squared. And so we get 1 minus sine squared of x to the 3/2. So we can rewrite the integral as sine to the fifth times 1 minus sine squared to the 3/2 power times cosine x dx. That part is the du. So now everything can be rewritten in terms of u. So we've got u to the fifth times 1 minus u squared to the 3/2 times du. And now let's stop here and do the same idea for the second version of the problem. So if we look at the second problem, or the same problem, but the second solution method, u is cosine this time. So we're going to try to create du at the end of the problem. So that means we need to take one of the factors of sine. There were 5 there, so that's going to leave 4. We're going to leave cosine to the fourth alone, and the fifth factor of sine we're going to put with the dx. So we're separating sine to the fifth into 4 factors of sine at the beginning and then 1 factor of sine at the end. Du is negative sine x dx, so we're going to multiply inside by negative 1. That means we also have to multiply outside by negative 1. Now we've got the du at the end of the problem. We want to now rewrite everything in terms of u, which is cosine. So sine to the fourth needs to be rewritten in terms of cosine. We can think of that as sine squared x squared. Sine squared is 1 minus cosine squared because of the identity at the top of the screen. It's called the Pythagorean identity for sine and cosine. So 1 minus cosine squared x squared. And so we're going to use that expression in the integral. So sine to the fourth of x gets replaced with 1 minus cosine squared times cosine to the fourth times negative sine x dx. We rewrite that using u and du. So we get 1 minus u squared times u to the fourth times du. So the steps to that point in both versions of the problem are basically the same. So now I want you to pause for just a second and look at the last step in each problem. Both of those steps have an integral that we now need to do. Think for a minute about which one would be easier to evaluate, or which one would even be possible to evaluate based on what we've done at this point. Okay, so the 3/2 power in this problem means that there's not a useful algebraic simplification. And so that's bad for us to continue working this problem. The 2 here means that we're going to be able to simplify this by expanding that polynomial. So to continue this problem on the bottom, we can square 1 minus u squared. That gets us 1 minus 2u squared plus u to the fourth times u to the fourth times du. And just as a quick review of algebra, what we're doing there is we're doing 1 minus u squared squared, so we're multiplying out 1 minus u squared times itself. That then lets you distribute u to the fourth. So we get negative u to the fourth minus 2u to the sixth plus u to the eighth du. We can do each of those integrals and the negative distributes. So we get negative 1/5 u to the fifth plus 2/7 u to the seventh minus 1/9 u to the ninth plus c. So I'm doing the power rule on each of those three terms, and I'm distributing the negative simultaneously. U was cosine, so we can rewrite this as negative 1/5 cosine to the fifth plus 2/7 cosine to the seventh of x and minus 1/9 cosine of x to the ninth plus c, and that is the answer that we would use for this problem. Okay, so this is the approach that we would like to take for any problem involving powers of sine and cosine. It's not always possible to take this approach. What we're going to look at is we're going to want either for u to be sine or for u to be cosine. In some problems, it has to be set up where u is sine. In some problems, it has to be set up where u is cosine. In some problems, both of those would work fine. And then in some problems, neither of those would work. And so we want to look at these two problems to determine what makes that work. But I want you to try a problem first, and then we'll come back and determine how do you make the decision between the two substitutions. So we'll come back to this screen in a minute. But I'd like you guys to pause the video and just try this. So if I have cosine or sine to the fourth, cosine to the third x. We're going to talk about how to know this in a little bit, but I want you to do this problem where u is equal to sine x and du then is cosine x dx. And so pause the video, work this out just so we get the mechanics of this down, and then we'll talk about how to know what substitution to make. Pause the video, try it, and check with me in a couple minutes. Okay, so if u is sine, du is cosine, we're going to leave sine to the fourth alone and try to create du at the end of the problem. We do that by separating cosine to the third into cosine squared times cosine. The cosine x at the end of the problem is for the du. Cosine squared needs to be rewritten in terms of sine. Cosine squared is the same thing as 1 minus sine squared. So now we can rewrite this as u to the fourth times 1 minus u squared times du. We can distribute u to the fourth and now do the power rule on each of those power functions. So we get 1/5 u to the fifth minus 1/7 u to the seventh plus c. U is sine x, so we get 1/5 sine to the fifth x minus 1/7 sine to the seventh x plus c. And that's the answer. Okay, so this is the strategy that we would like to use every time. How it doesn't work every time, but let's now figure out when this is going to work. Okay, so the thing that made the problem up here not work on the first solution was the 3/2 power. So if we get a fractional power there, then we get to a form where it's not useful to continue the problem. So the 3/2 power, let's trace that back. The 3/2 power here came from up here where it was cosine to the third. So the fact that it was cosine to the third forced this to be 3/2 power. The 2 down here that was good, that came from over here where we had sine squared squared. And so sine to the fourth is where that came from. So the fact that that 4 was even meant that this was going to work. The fact that the 3 up here was odd meant that this was not going to work. The 3 there came from the 4 in the beginning. The 4 here, whoops, sorry, I circled the wrong one down here. So the 4 here didn't matter. It was the 4 on the sine x that mattered because that's the one we rewrote. So this 2 came from this 2, which came from that 4. The reason that was 4 was because that was originally 5, and we split off one of the sine x's. Okay, so when you're doing this, the one that you need to rewrite needs to end up with an even power. Okay, so the one that you need to rewrite needs to end up with an even power. Well, the one that you need to rewrite for sine and cosine is going to be the one that is not u. It's going to be the one that is du. And so because we need like this to end up with an even power, we've separated one of them. So that means it needed to start with an odd power. So the one that is not u needs to begin with an odd power for this to work. Here, when u was sine x, the one that was not u had an even power, which is how we knew this was not going to work, or how I knew this was not going to work before we begin with, or before we started. That's how we want to notice that later. So on the next problem, the fact that cosine had an odd power meant that that was a good choice for du, because then we ended up with cosine squared here. That even power allowed an understood 1 here. The fact that that was not 1/2 or 3/2 or 5/2 meant that this was doable. So the quick rule for powers of sine and cosine is powers of sine and cosine. If one has an odd power, let u equal the other one. Okay, and so a couple things about this statement. It's stated very, very specifically. So one thing it does not say is it does not say that you let u equal the even power. Okay, there's no guarantee that you're going to have either function with an even power. And so it's not always that you do that. If they both have an odd power, it doesn't matter which choice you use. You can set it up either way. You could let u equal sine or u equal cosine. The other thing is that this is for problems that look like this. So it's where we have the integral of sine to the m of x cosine to the n of x, where m and n are positive integers. So when it's like 1, 2, 3, 4, 5. There are some other problems where this may work, but this always will work when m and n are positive integers. So if one of them has an odd power, let u equal the other one. It is not saying to let u equal the even one. So if they're both odd, you can do either one. If cosine has an odd power, you let u equal sine. If sine has an odd power, you let u equal cosine. The case that we've not covered is if both of them are even. So I want to look at a couple problems where we do that. So if both are even, we use what's called half-angle identities. Whoops. Use half-angle identities. Okay, and so the half-angle identities, these are modified versions of ones from trig, but half-angle identities are sine squared x equals 1/2 times 1 minus cosine of 2x, and cosine squared x is 1/2 times 1 plus cosine of 2x. These should be used very deliberately in problems. When we're doing powers of sine and cosine, like sine to the m, cosine to the n, the only case when you would use these is if both sine and cosine start with even powers. There may be more complicated integrals where you would want to use these identities, but for these standard problems where it's sine to the m, cosine to the n, where m and n are positive integers, the only case you'd be using these two identities is if both of the powers start as even. So let's look at problem 3, I believe we're on. And let's say, okay, problem 3 is cosine squared of x. All right, so when we do this integral, again, we look at this as being powers of sine and cosine, even though sine's not there. Sine is to the 0 technically, cosine is to the 2. And so the idea is if one of them has an odd power, let u equal the other. Well, 0 and 2 are both even. So then, okay, if both have even powers, then we're going to use the half angle. So the half angle identity lets you rewrite this as 1/2 times the integral 1 plus cosine of 2x dx. We can now split that into two integrals. So 1/2 times the integral of 1 dx plus 1/2 times the integral of cosine of 2x dx. The integral of 1 dx is x. The integral of 2x, or cosine of 2x, is 1/2 sine 2x. So we get 1/4 sine 2x. Let's neaten this up just a little bit. Sorry about that. That's dx. All right, and so we get 1/2 x plus 1/4 sine of 2x plus c, and that's the answer. It's important to notice that the half-angle identities do not actually evaluate the integral for you. They're a way to rewrite the trig function, so the integral sign does not go away when we deal with that. Okay, let's look at another example. So we'll do the integral of cosine to the 4th. I'm sorry, let's do sine to the 4th x dx. All right, so again, this is powers of sine and cosine, but both powers are even because sine is to the 4th, cosine is to the 0. So we're going to use half-angle identities. When we do that, sine squared of x, we think of as being sine to the 4th of x, we think of as being sine squared squared. And so then the entire identity on the right-hand side gets squared. So we get 1/2 times 1 minus 2x, or cosine of 2x, all squared. That gets us 1/4 times 1 minus cosine of 2x squared. So the first step on the integral is we're going to pull the 1/4 out and rewrite the rest of this as 1 minus cosine of 2x squared dx inside the integral. We can expand that by distributing. So we get 1 minus 2 cosine of 2x plus cosine squared of 2x dx. We get that by multiplying 1 minus cosine 2x times itself and distributing. And so if you need to do that on the side, you can, but that's what we get when we distribute it. We're going to separate that into 3 separate integrals, and the 1/4 is going to carry on to all 3 of them. So we get 1/4 integral 1 dx minus 2/4 or 1/2 integral cosine 2x dx plus 1/4 integral cosine squared of 2x dx. Okay, so let's get rid of this side work. But now, when we look at this, we've got 3 separate integrals to deal with. The first one's very straightforward, so the integral of 1 dx is just x. The second one is a very quick u substitution, where u is 2x, so we're going to get 1/2 sine of 2x. The third one is powers of sine and cosine again, where both powers are even, and so we're going to use half-angle identities. So it's important to notice, though, that when we use the identity cosine squared x, over here we get cosine of 2x, and same thing here, when we have sine squared x, we get cosine of 2x. That's very easy to apply, but it's easy to mess up, so let's be a little bit careful there. So whatever is inside of here, if this was 7x, then this would be 14x. So it's double whatever's there. When the one on the left is 2x, the one on the right is 4x. And so we want to just be careful of that when we're applying the identity in this case. So let's scroll down a little bit and work this further. So we get 1/4 x for the first integral. I'm going to leave this as 2/4 just so it's clear that where that's coming from, but then we get a 1/2 from the u substitution that we're just kind of doing in our head on cosine of 2x. And then we're going to use the identity here and get 1/4 times 1/2 times the integral 1 plus cosine of 4x dx. Now we're going to simplify this down a little bit and split the last integral into 2 more integrals. So we get 1/4 x minus, here we get 1/4 because it's 1/2 times 1/2. And now we get 1/8 integral 1 dx plus 1/8 integral cosine of 4x dx. We're now going to evaluate both of those integrals separately and do some small simplification. So 1/8 integral of 1 dx is 1/8 x. On the last one, we get 1/32 sine of 4x because it's a quick u substitution where u is 4x and du is 4 dx. So then we multiply inside by 4 and outside by 1/4. 1/8 times 1/4 is 1/32. So then we combine the 1/4 x and the 1/8 x. That's 3/8 x because of a common denominator, so we get 2/8 plus 1/8. And aside from that, there's not much useful simplification that can be done. And so we get this answer, 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus c. Okay, so I'm going to put another problem up, and I'd like you to pause the video and try the problem. So number 5 is going to be the integral of cosine to the 5th x dx. So pause the video, try this using whatever method we can use that we've covered in the video today, and then check it with me in a few minutes. Okay, so on this problem, it's important to notice it is powers of sine and cosine. Sine is technically to the 0 power. Cosine is to the 5th power. And so the quick rule is that if one of them has an odd power, then u should equal the other one. So it's weird, but on this problem, we're going to let u equal sine of x. Du then is cosine of x dx. it's weird to let u equal sine x because u isn't in the problem, but let's work through and see what happens. So to get du, we're going to split off one of the cosines. We're going to reserve that cosine for du, and we're going to rewrite cosine to the fourth in terms of sine. So this is why this will work out, because now this is in terms of u. So we get 1 minus u squared squared times du. We expand that and get 1 minus 2u squared plus u to the fourth du. That's now 3 power functions. The integral of 1 du is u. We then get 2/3 u to the third and 1/5 u to the fifth. We replace u with sine x. So we get sine x minus 2/3 sine x to the third plus 1/5 sine x to the fifth. And that works on this problem. Okay, so you should have a worksheet with a lot of practice problems that involve powers of sine and cosine. Definitely worth going through those. The next video will be on more trig integrals where we use similar techniques to evaluate integrals involving powers of secant and tangent. All right, thanks for watching the video.